All right. Morning, y'all. So just so reminder, I just totally forgot last week about having a quiz, but it didn't really matter. I was basically just putting on like an extra. Yeah, it's not gonna be a big deal. So we will in fact have our first quiz Friday, and it will just have 2 learning goals on it, which is so L1 is about making truth tables. So hopefully at this point you should have had plenty of practice doing that. And L2 is about using algebraic laws to simplify propositional logic things. And so that we've covered more recently. But again, like, if you feel prepared to do that, on Friday, then you can do it. And if you don't feel prepared, you could attempt it and be like, maybe I understand it better than I think, or just leave it blank. You don't have to do it, right? You're going to have multiple opportunities to demonstrate that you understand that learning goal. So, does that make sense? Yeah, go on.
Will we allow like a little cheat sheet of all the simplifications?
Nope. No, you need to know it. You don't need to, remember, you don't need to memorize the names, but you do need to know like what kind of manipulations you're allowed to do and what things you're not. Yeah, and again, right, you don't need to memorize the names. You don't need to, like, if you kind of do multiple steps at once and you don't explicitly call out like each individual step, I don't care. If you make a tiny mistake here or there, like if you miss some parentheses or something, like, I'm not gonna, if you can demonstrate to me that you fundamentally understand how to manipulate these expressions algebraically, right, that'll be it. So that'll be like basically at the end of class, like the last 10 or 15 minutes of class or something. My intention, I'll just say this, and if this applies to you and you want to talk more, you can come talk to me, but my intention is to leave enough time for the quizzes that, like, they're kind of designed to take, let's say, 5 minutes, right? And so even if you have an accommodation where you get like extra time for quizzes and stuff like that, it should be enough time. But if you feel like it's not, right, come talk to me and we can figure something out. But that's sort of the intention. I'll put it at the end of class, leave plenty of time so you can do it. And if you just do it and you're finished, you can just leave. You don't have to sit there till the end of. That's why I put it at the end of class, so you can just leave. All right. But again, so L1 is actually going to be on the next 3 quizzes. And in general, each learning goal will be on 3 quizzes before it rolls off. But even if you miss that, there's still other opportunities. You can come to Ox Hours, or you can wait for the final quiz at the very end. All right. So we are going to talk about predicates and quantifiers. So basically, at this point in our study of propositional logic, we have essentially caught up with the ancient Greeks. And so there's a bunch of stuff that we can express, and certainly being able to manipulate these things algebraically. I mean, okay, actually we've gone beyond the ancient Greeks. They didn't really have, a whole theory of like how to manipulate these things algebraically, right? We've caught up with like the ancient Greeks and Boole, basically. But there's one important missing part where there's things that we want to be able to say that we can't say. Right, and in English we make statements like this all the time. So either universal statements where we use words like all or every or each, right? We're making like a blanket statement that something is true, some proposition is true for every member of some group, right? We also make sort of existential statements where we say, well, this isn't necessarily true for everyone or everything in this group, but it's true for something, like at least one, right? And those kinds of statements turn out to be, they come up all the time in mathematics and computer science. So I'm going to talk about how we make that formal. Okay, so in order to, I was hoping this was going to work, but maybe it'll work. So we're going to start talking about, because if we want to be able to make these kinds of statements, we need to be able to have propositions that can talk about multiple individual items. So in other words, we need to be able to have propositions that are kind of parameterized by a thing that we're talking about, right? So if I write down something like, it's very frustrating. I have this nice like stylus that works most of the time, and just like every, like half a second out of every 5 seconds, it just like stops working and doesn't make a mark. And all right, so I have to use this like tiny little stupid one that comes with my computer, but that's fine. So if I write something like this, x plus 2 equals 5. Is that true or false?
Depends on what x is.
It depends on what x is, exactly. So I would say, by itself, that is not a proposition. Because whether it's true or false, it's kind of like not quite defined. Like it depends on what x is. Certainly, if we have in mind a value of x, then this is a perfectly good proposition. Okay. So we'll say this is not a proposition on its own. It depends on x. Okay. But so let's we can define. It's almost a proposition. It wants to be a proposition, right? But it's just kind of waiting for a value of x to be filled in, and then it will be either a true or false statement. So we can define, for example, I'm going to put this in quotes just because otherwise the different equals signs are confusing. I'm going to define, p of x. So I've defined a thing called p, which takes x as a parameter, and then gives us this proposition, x plus 2 equals 5. Okay, so this is called a predicate that takes x as a parameter or input and results in a proposition. I'm not going to be super pedantic about the distinction between a proposition and a predicate. Again, these are just words you might hear. We could also just call it a proposition and say, well, some propositions, have inputs or they're kind of parameters. So, for example, right, P of 2 is a proposition, right? It is the proposition that 2 plus 2 equals 5, right, which is false. So this is a false proposition. 2 plus 2 equals 5. And P3, that is a true proposition, right? It's the proposition that 3 plus 2 equals 5. Right, and in general, any value I put in for x will give me a proposition. Almost all of them are false, right, except if I put a 3 in. But in general, you could imagine things that are true for more values of x, right? Okay. And actually, I just want to show you really quick that we can do this, and let me make this bigger here in Disco. So if I say like, right, so in Disco, remember we can do :test, and then we can write down some proposition and it'll like test it for us to see if it's true or false. So for example, just to show, if I said, hey, test this proposition, x plus 2 equals 5. Of course it's an error. It says there's nothing named x. I don't know what x is, right? But we could define, let's say we're going to define p which is a function that takes a natural number and returns a Boolean. And I could define it by p of x equals x plus 2 double equals sign. Now remember, right, in Disco, we use a single equals to define something, and then we have to use the double equals to say, like, I'm asking, are these two things equal or not? But if we do that, we can say, like, okay, now test, p of 2, and it'll say that's false, right? Or we could say test p of 3, and it will say that is certainly true, right? We can also, while I'm over here, we can even make, so this is a predicate that takes one input, right? We can certainly make kind of multi-input or multi-parameter predicates. So I could say, and don't worry too much about the syntax here, we'll talk about this more later, but for now you can just take my word for it. This is how we can make a function that takes like multiple inputs. Basically this is saying it takes a pair of natural numbers as input and returns a Boolean. And I can define it by saying, for example, t of x comma y is the proposition that x is less than y squared, for example, right? And now I can say, t of 3, 5. I think that should be true because 3 is less than 5 squared, right? Oh, what happened? Oh yeah, okay. Because t is true. I can't redefine t. Let's give it a different. I had it. It was called t in my notes, but I didn't.
True. Yeah.
Yeah. Let's call it q. No, j. Try it again. All right. Hello?
We're gonna find this good take.
Reload. Maybe. Okay, so apparently we're finding some bugs here, but that's okay. Let's try again. Okay, this is true if I say test, yeah. So I noticed I added the clear history button that some people were asking for. But I also just, as I was doing this, I realized to warn you, and maybe I can think about whether this is fixable. Like if you just hit reload on the page, you'll lose any code that's over here.
Yeah.
It's just gonna like poof, be gone. Probably that's fixable. I don't know off the top of my head how to do that, but certainly there are websites that do that where you reload and it'll still keep the stuff.
I think it would have to involve cookies.
I mean, if you need to reload, then of course you can always copy paste it or save it first or something. Okay, with cookies, yeah, I don't know how that works. Maybe. But as 3, 0, that should be false, right?
Yeah.
Yeah, certainly false. Okay, cool. What questions do you have at this point? Yeah, Spencer.
Where's this hosted at? Like the online version of this?
What was that? Where is it posted? Well, the easiest way to get there is there's a link from our course website. If you just click on this Disco Live, that'll get you there. Okay. Alrighty. So. Now that we have that, we can use that to define. So we're going to start with something called the universal quantifier. So these things, like, we're going to learn about two things called quantifiers. They're called quantifiers because in some limited sense they let us quantify how many things something is true for, right? Now I say limited because we can't say like it's true for 6 things. We only have 2 options. We can say it's true for everything or it's true for something. But it turns out that those by themselves get us pretty far. So let me just define it for you, and then we'll just look at a bunch of examples. And we've actually seen this before a little bit when we saw some disco tests that used the word for all. Okay, and that was a universal quantifier. So if Px is a predicate, right, so that is one of these parameterized propositions, and D is some domain. I'm being vague about what a domain is, but you could say it's like a collection of values. Values, or a type, right? Like in disco, we have these types, and types are collections of values, essentially. Then, so we're going to write, so this symbol is just an upside down capital A, okay? And we read it as for all. So I'm going to say for all x colon D, and I'm going to put a dot, Px. Okay, and this is pronounced for all x in D, Px. So this is a proposition. Let me put this in parentheses. And I have to say, if it's a proposition, I have to tell you when it's true and when it's not true, right? It is true if and only if P of x is true for every x in the domain D. I will just note sometimes you will see the notation like using this symbol instead of a colon. We're gonna see that symbol come up again in a few weeks. It doesn't really matter. Right now it's just a symbol. I prefer using a colon, but it doesn't really matter. D is called, well, okay, no, let me not say that. I will just say, I'm not going to spend too long on this. Sometimes, if you look at certain textbooks and stuff, sometimes mathematicians just omit writing the colon D part. They just write for all x, Px. And you're just supposed to understand from context what the domain is that is being talked about. And I think this is a horrible idea because, like, what domain you're talking about this is an essential part of what this proposition is saying. Changing the domain can make it be true or false, right? So if I say, all students at Hendrix are studying discrete math, right? That's not true. But if I say all students in this room are studying discrete math, that is true, right? So, but just by changing the domain, you can make it be true or false. So what the domain is matters a lot, and so we need to include it as part of the notation. That's all I will say about that. Let's do some examples. Here's a first example. So, I'm just going to say Pn. So Pn is defined as above. So, you know, Pn is defined as, you know, x, or, well, in this case, n plus 2 equals 5, right? By the way, what variable we use, like if I say px or pn, it doesn't matter. Just like when you're defining a function in some programming language, you can call the inputs whatever you want. It doesn't really matter. So, is this whole proposition, is it true or is it false? Let's vote. How many people say it's true? How many people say false? Okay, good, correct. Yeah, so what is this saying? It's saying that Pn is true for every natural number, right? That's clearly not the case, right? P3 is true, but there's a bunch of other numbers that it's not true for, like, for example, 6. And actually, just telling you one number that it's not true for is enough to show that this is false, right? Because this claims it's true for every natural number. So if I can say, it's not true for every number, how about 6? You're like, oh, you're right, P6 is false. So yeah, okay, you're right, it's not true. So this is false. Here's another example. Actually, I'm just going to write down 3 examples, and I just want you to chat with your neighbors and come to a consensus on whether you think they are true, each one is true or false, okay? All right, so go chat. Decide whether these are true or false.
I believe all of
Oh, no. I was thinking step for PM. So, for all natural numbers, what about 0? Is 0 a natural number? That's, it's just, it's like the conjecture. Yeah. Z X is X. That's integers. That's integers. It's not true. No. And then any integer squared by itself, so that would make it true. That would make it positive, so it would make it true. Yeah.
All right, so what are we thinking? So how about this first one? For all natural numbers n, or for all n in the domain of natural numbers, n is greater than or equal to 0. Is that true or false?
It's true.
That is true. Every natural number is 0 or bigger. So this is true. How about this next one? See some thumbs down. Is it false? Why is it false?
Might be negatives.
Yeah, Brayden?
Integer includes the negatives, right?
Right. Yep.
So it'll be like if you go further down negative, plus 2 on anything, you know.
That's right, yeah. Yeah, so for example, you know, minus 134, that's an integer, right? But this is not true. I put in that number here, so. This is false. And how about this last one? True or false?
It's true.
That is true, right? 'Cause when you square an integer, you always get something greater than or equal to 0. Okay. Cool. All right. Okay. And I will just show you, right? So in Disco, we can try out these same ones in Disco. So if I say test, so you can actually, use this symbol in Disco if you want to copy paste it from somewhere. You can also just write the word for all. So I can say for all n dot, well, I guess I do have p here, right? So I could say pn. Say, let's test that proposition. And it says that is certainly false. And if a for all is false, right, we can show that it's false by giving a specific counterexample. There's an example where it's not true. So it says, hey, I found a counterexample 0. So this is supposed to be true when n for all natural numbers, but when it's 0, Pn is not true, so it doesn't work. Okay. What was the next one we had? For all natural numbers, n is greater than or equal to 0. So this one is interesting. Notice what Disco says. It says it's possibly true. It checked 100 possibilities and it did not find a counterexample, right? Because there's infinitely many natural numbers, right? Disco can't actually check all of them. Now you might say, well, in this case, you could certainly imagine some computer program being able to know for sure that this is always true, and there certainly exist such programs that could check things like this and be like, oh, I just know some facts about natural numbers, and I know that this is always true. Disco isn't doing anything that sophisticated. If you test a for all, it's just going to try a bunch of examples, and if it finds one where it's false, then it knows for sure that for all is false, right? But if it tests a whole bunch and they're all true, it's like, well, it might be true. This is maybe some evidence that it's true, but it's not a proof. So let's see, if we test, if I change it to integers, right, then it finds a counterexample. It says, hey, if -1 is a counterexample, -1 is not greater than or equal to 0. But again, if we say, how about if it's squared, again, it'll say, well, it might be true. I checked a bunch of things and didn't find any counterexamples. Okay. Questions about that? Yeah. Yeah.
Sometimes just for my testing, like the whole left side, right side thing wouldn't appear. Is that like, what cases does that not happen in?
Well, it's when you're testing something that specifically has some kind of comparison operator, like if you're saying, is this equal to that, or is this greater than or equal to that, or something.
Okay.
Notice in this case, it didn't say the left side, right side, because there is not a left side or right side. It's just like Pn. Now, I guess you're like, well, Pn itself consists of an equals. But I think since it's not, we didn't literally write out
Right.
equals here, it doesn't say it, because I don't know, it might be confusing if you're looking at this and you're like, what's the left side and the right side? Yeah. I think. I'm like 95% sure that's the right answer. I haven't actually worked on this. Actually, I worked on this a long time ago, and I actually had a student, like all this stuff about it being like possibly true or certainly true, or like a student actually added all that. Like before it would just say false, true. And then a student added a whole bunch of stuff so it could like kind of keep track of what it knew for sure and kind of what the evidence was and could show that to you. So, yeah.
I don't know if this really matters, but like, which type of, is it again where 0 is kind of, it might be in that set, like?
Oh, for us, 0 is, like the natural numbers does include 0.
Okay.
But I think, yeah, what I said is, like, depending who you talk to, if you say the natural numbers, depending who you talk to, that might include 0 or might not.
Okay.
Yeah, although, in this case, whether this is true or not doesn't depend on whether 0 is in there or not, right? Even if the natural numbers did not include 0, this would still be true for all natural numbers. But yes, it does. Natural numbers does include 0. Okay. All right. So here. So here's. I've given you a definition of for all, but I want to tell you another way to think about it that can sometimes be helpful. It's not a definition, but it can be helpful to think of for all as a big and. And what I mean by that is if we have something like for all x in some domain p of x, it's kind of like saying, well, p is true for, x1 and p is true for x2 and p is true for x3 and ... where we just list all the elements of the domain D, and the elements are called x1, x2, x3, right? Right, because this is how AND works, right? If these are all true, then when you do the big AND of all of them, you're going to get true. But if any single one is false, it kind of spoils everything, and the whole AND is going to be false. And that's exactly how for all behaves. Again, this is not the definition, primarily because we want this to work to make sense even if the domain is infinite, and it doesn't really make sense to write down like infinitely many things with AND, right? But it is a really helpful way to think about it sometimes, and we can use it to kind of help us deduce some properties of how for all works. When we think about it, we can think about it in terms of AND. Okay, so on that note, I'll look at another example. I'm going to define the domain H to be Hendrix students who are over 11 feet tall. Okay, and I'm going to write down a proposition for all H in the domain H. H plays varsity pickleball. My question is this proposition true or false? Discuss with your neighbor. Decide whether you think this is a true proposition or a false proposition.
With the second correlation image, it's 0. Pickleball. I'm thinking too hard about this. I don't think. It was good that I actually played engagement that time. What is the importance of the stream? Plays Washington. That's still engagement. H play for all Hendrix for all H. H for all Hendrix. No. Wait, what is H? Like lowercase h. One second. For all H would be, H isn't defined. I'm assuming, like uppercase H's. Well, I don't think it matters that much. Maybe. I don't think this is true because I don't think H is defined. And so in that case, you can't say like everybody is playing a pickleball.
All right, so let's hear some thoughts. Yeah.
The lowercase h and the uppercase h, two different values.
They're different, right. So uppercase H is defined right here, and it represents this domain, some collection of things, right? Lowercase h is defined right here. Lowercase h is just the variable I'm using to stand for one thing in that domain,
Okay.
right? So whenever you say for all variable : domain, right, this variable, you're just kind of like defining it locally to stand for, any one thing in that domain. Does that make sense? So this lowercase h would represent one student that's in this domain.
Okay.
Yeah. Jack?
If the domain presumably has no values, there's no counternumbers.
Okay, so you're saying, whoops. Yeah, so this domain, and this is the strange thing, of course, about this example. The domain is, I presume, empty. I don't know any Hendrix students over 11 feet tall. Maybe do you? I don't think there are. And so this really comes down to like, what does this even mean to make a statement about every member of a domain when that domain is empty. So Jack, you said there's no counterexamples, right? So what do you think that?
I think it's true.
So you think it should be true? There's no counterexamples. You all agree there's no counterexamples? Like a counterexample, right? So one way, if you have a for all statement that we've seen, to show it's false, you're like, well, you said this is true for everything in this domain, but look, here's a specific member of the domain where this is false. So it's not true for everyone. But there's certainly there's no individual student over 11 feet tall that we can point to and be like, look, that student doesn't play varsity pickleball, right? Because there just aren't any such students. So there aren't any examples, but there aren't any counterexamples either, so maybe it should be true. I don't know, any other thoughts?
The counterexample would be not playing pickleball.
Yeah.
I don't know.
Like if nobody is playing pickleball, is like,
But
if
then
we
that's
have
saying,
nobody.
what if there's people who play pickleball but aren't?
Yeah, I mean, of course, that's the other funny thing about this example is that we also don't have a varsity pickleball team, so like, this couldn't be true of anyone, but I did that on purpose because...
It's just like it requires external context.
Yeah, okay, right. This is not a mathematical statement. I was trying to pick examples that we would all agree. Like, there definitely are no students that are over 11 feet tall. Okay, so I'll say this is strange because H is empty. What should for all mean with an empty domain? And I want to stop and emphasize at this point that, because, depending on the experiences you've had in math, probably in many cases you've just been told that something is the case, like this is the correct answer, and you were just expected to just believe that that was the correct answer, and you're just like, all right, well now I know what the right answer is. And so on one level, I could just tell you, this is whether it's true or false, this is the right answer. And there is a correct answer in the sense of kind of what, pretty much the vast majority of mathematicians would agree about this. However, I want to make the point that it's not like, someone 300 years ago just arbitrarily decided what the correct answer would be, and then from then on everyone was like, okay, I guess that's the right answer, I guess we just have to go with that, right? There's a reason that the answer is what it is. It's because if you pick that as the answer, a lot of other things work out really elegantly and nicely. It's sort of like when you start learning about all these things around it, you're like, it really feels like it wants to be this and not this. Like if I make it this, everything works out really nicely. And if I make it this, we could just say, well, we're just going to define it to be one thing or the other, or we're just going to say it's not defined, right? We could say that, but there's an answer that's going to make things work out nicely, and that answer is indeed this is a true proposition. So, and that's maybe somewhat counterintuitive, right? But I want to give you a couple ways to think about why this is true. So. One way that Jack already pointed out, there are no counterexamples. So, if it's not false, it should be true. And again, I'm not trying to give like logically rigorous arguments why it's true. I'm just trying to kind of reasons that you're like, yeah, that maybe feels like maybe this should be true. Here's another reason, right? So remember I said before that a for all is like a big and. We're going to take all the things in the domain, and for each one we're going to like and them all together. So if you do an and of 0 things, what should you get? And the answer is true, because true is the identity element for and. So just like if you have a set of things, but there's nothing in this, like no numbers in the set, and you're like, what do I get if I add them all? You should get 0, because 0 is the identity element for and. It's like if you haven't done any adding yet, you just start with 0 because that's the identity, right? If you haven't done any anding yet, you should start with true because that's the identity for and. So I'll write this down. If for all is like a big and, what should you get if you and together 0 things? Oops, things. True, because that is the identity element for and. Right, and we saw this the other day when we that was one of the laws that we said P and true is P because true is identity for and. Anyway, and I think I mentioned this on maybe the first day of class. This is one of these themes that we're going to see coming up in a bunch of different contexts. It's like we're going to encounter something where we have some definition, and then we're like, well, but what if something is empty, or what if something is 0? What if something is false? What should the definition mean then? And one thing we could do, and one thing some people do is they just say, that's weird. Let's just say that's not defined. But in most of those cases, well, all the cases that I know of really, there is kind of a right answer in the sense that there's an answer that makes everything work out really elegantly. And so we're not going to be afraid of those cases where things are empty or 0 or whatever. Okay. Got a little bit of time left. So the other quantifier is this is the universal quantifier for all. The other one is called exists. So this is the existential quantifier. But now that we've talked about for all, I think this one's going to be a little easier. I'm going to be able to do this a little more quickly. So if Px is a predicate and D a domain, then, so for all we write with an upside down capital A, exists we write with a backwards capital E. I mean, I think it's literally like all A, so we just take the A and do something funny to it to make it into a different symbol, and the same thing, exists starts with the letter E, and so we just so these ones are pretty easy to keep straight because it's just like, oh, it's a backwards E or upside down A. So exists X in the domain D, Px, which is pronounced there exists, and X in D such that Px. So this is a proposition which is true if and only if there is at least one X in D such that Px is true. Okay, there could be more than one. More than one is fine. Could be all of them. I don't know, but there has to be at least one for this to be true. Okay, so let's do some examples. Let's say there exists a natural number n such that Pn, remember Pn is the one that says n plus 2 equals 5. So is this true or false? This is true, right? There does exist at least one natural number that we can put in there that makes P of n true, specifically 3. Right? That's actually the only one, but 1 is enough. So this is true. I'll say P3 is true. What other examples do I have? Here's one. So there exists an x, which is an integer, such that x squared equals 16. Is that true or false? That's true, right? Actually, there's two integers that make this true, 4 and negative 4. That's fine too, right? As long as there's at least one. So this is true. For example, 4. Okay, what if I said there exists x, which is an integer, such that x squared equals 17? Is that true or false? False. This is false, right? And it matters here for sure that I said integers. Right? If I said like real numbers, okay, well now there is a real number whose square is 17, but there's not an integer whose square is 17. Right, so this is false. Right, no integers. I can't spell. Integers square to 17. Okay. And I think okay, I got two more examples which are a little more tricky. I'm going to write them. We'll see if we can get through them or if we need to. So I want to use 2x less than y squared. Okay, so this one's a little more tricky, right? Because I've actually used both a for all and an exists. So remember, like this by the exists y blah blah blah, like that is a proposition. And so I could put another for all outside of it, and that also is a proposition, right? So I can stack these and nest them as much as I want. And maybe just to be clear, I will write it with parentheses. We don't need to write the parentheses, but I just want to make clear how they're nested, right? So this is saying for all x, for all natural numbers x, this is true. Right? So no matter what x you pick, this statement, this proposition, which itself has and exists, right? But this proposition is going to be true. So what do you think? Is this true or false?
False.
False? Why?
0 or x equals 0 and y equals 0. I mean the
So you're saying when x is 0, it's not true, Maggie?
You could have x equals 100 and y equals 3.
Yeah.
And 100 is not less than 1.
right.
You could have x being 100 and y being 3. Well, okay. So when x is 100, so this is a for all. So this needs to be true when x is 100, right? Is this true when x is 100?
Yeah.
It is, because this doesn't exist. We only need one natural number that makes this true. So, and we get to pick it to be whatever we want. So if x is 100, yeah, we could pick y to be 100, right? 100 is less than 100 squared, and so for x being 100, there is a natural number that makes this true. So one thing to point out, like, this is, I mean, technically this is already implied by what I've said, but it's something you needs thinking about. For each x, we get to pick a different y. Right? For each x, this whole thing has to be true, and for this to be true, we can pick whatever y we want. We don't have to like pick a single y that works for everything, right? And so like, you know, when x is 7, I can be like, all right, when x is 7, I'm going to pick y to be 20. And 7 is less than 20 squared, so that's true, right? When x is 99, I'm going to pick y to be 1,000, and that'll make it true, right? So is this true for all x?
Yes.
No? Yes?
Because if you were to do an x, let's say x is 20 and y is 3, then
No. So remember, if I pick x to be 20, I need there to be some y
Oh, okay. I see.
that makes this true.
I see.
You're right, it's not true for 3, but that doesn't matter. As long as there's at least one y that makes it true, and there is, right? I could pick y to be 900, right? Yeah. Yeah, so if this were a for all, right? If this said for all x, for all y, that's not true, right? Because then it has to work no matter what x and y you pick, right?
I see. It's just a big mistake.
Yeah. So I think this is actually true, right? So like when x is 0, is there a y that, yeah, you could pick y to be 1, for example, right? So no matter what x I pick, I can always pick a bigger y that will, where x will be less than y squared. Okay, we're out of time. But this is true. All right, I will see you all on Friday.
Makes sense. Is there go today?
Yeah.
Jen's